All right, welcome everyone. In this lesson, we're going to be looking at exponential growth, and we're probably going to get to the decay part of this in class or maybe next time. So we're going to start with our motivating example for exponential growth. And this is going to be maybe a population of a bacteria culture that doubles in size each day. And initially, one bacterium is present. And what we're going to do is we're going to try to figure out the size of the population after 3 days. And ultimately, this is going to relate back to an exponential curve. All right, so let's try to just think about what's going on with this population. Let's think about how this is going to grow over these 3 days. And so let's kind of think about, well, what are we going to start with? At time 0, what's our bacteria culture going to look like? And then what about after 1 day? What about after 2 days? And then what about after that 3rd day, when the 3rd day ends? All right, so we have right here our initial condition that tells us we're going to start with one bacterium. So when we do this, let's kind of draw it out. Let's say, here we go. On day 0, when we start looking at this thing, we have one bacterium. All right, so where do we go from there? Well, the population of this bacteria culture is going to double in size each day. All right, so on day 0, we're starting with one bacterium. Well, that means after 1 day, we're going to double. So we're going to have 2 bacteria. So let's draw that in. So we're going to have 2. All right, and what happens is on day 0, we have one bacterium, and this thing splits into 2. All right. Well, then another day goes by, and we're looking at day 2 now. So what happens here is that each of these bacteria that we had before, each of these is going to split. So the one bacteria is going to split into 2. So we're going to end up with 2 bacteria from that one. And then our other one's going to split. And we're going to end up with 2 more bacteria. All right, so far, each day our population is doubling. So on day 2, we're going to have 4 bacteria. Well, then what happens after another day? Well, now we have 4 bacteria, and each one of these is going to split up into 2. So our population is going to double again. So we're going to end up with 8. So just a little picture. We're going to end up with 8 bacteria here. And what happens is this bacteria splits up and gives us these 2. This bacteria splits up and gives us these 2. And then each one splits up and we double. All right. All right, so on day 3, we have 8 bacteria. And we're going to want to generalize this type of thing, not just for this specific case where we're starting with 1. We're going to want to generalize it beyond this. And so we're going to call our starting population P0. And then what happens to go from day 0 to day 1, well, that starting population doubles. So we're going to take our starting population, which we're calling P0, and we're going to multiply it by 2. And then to go from our population from day 1 over to our population on day 2, it's going to double again. So we're going to take this previous population and double it up. So we're going to end up with P0 times 2, and that doubles, so we get another multiplication by 2. And then the same thing for the last day. So on our next day here, day 3, where our population is at 8, well, what happened is we took our previous population and we doubled it. So we went from 4, we doubled it up to 8. So we're going to take our previous population, which is here, and just multiply by another copy of 2. So we end up with P0 times 2 times 2, and then we multiply by another copy of 2. And so if we kind of clean this up, our starting population is P0, which we could really write as P0 times 2 raised to the power 0, because any number raised to the power 0 is 1. And then on day 1, our population is P0 times 2 raised to the power 1. And then on day 2, our population is P0 times 2 squared. And then on day 3, our population is P0 times 2 raised to the power 3. And so these exponents, 0, 1, 2, 3, those aren't coincidence that our population is doubling every day, and these time values are kind of represented in the exponents here. And what we see is that these kind of population sizes, they actually fit onto an exponential curve. So on day 0, our population starts at 1. Then after 1 day, our population is at 2. Then after 2 days, our population is at 4. And then after 3 days, our population is at 8. And so these data points that we have are falling on this exponential curve. And so this kind of sets us up for the idea of looking at population growth. So a population, or really any quantity that is growing exponentially, well, it's said to be growing exponentially, if at every time t, the rate of increase of the population is proportional to the size of the population. All right. And so if we know something is growing exponentially, well, the formula for exponential growth is P of t equal to P0 times e raised to the k times t. And what we were seeing in our little motivating example here is really more of an alternate form. This is the one we're going to be using because the natural exponential function is kind of nice to work with when we're talking about derivatives. But when we were setting this up, there is an alternate form to this. And conceptually, this one might be a little bit easier to relate back to our motivating example. So the population size, which we call P of t, and it's going to be a function of time, is equal to the initial population, so P0, times 2 raised to the power t over capital T. All right. So let's just talk a little bit about all the different terminology here. And we're going to kind of see how these two are related and all of that. So let's start with the first thing. What do we mean by P of t? Well, P is going to represent our population, and our population is growing over time. So really, population is going to be a function of time. So that's what P of t represents. This is going to tell us our population, the size of our population at time t. All right, so that's the first thing. And we've talked a little bit about it, but this P0, that's our initial population. That's how much we start with. So this is the initial population at time t equals 0. So this is what we start with, essentially. And the k value, so we know what e is. E is just a fancy number. T is going to be the variable for our function. And so the other quantity here that we have to talk about is this value k. And this k is called the growth constant. So this tells us, this kind of relates how fast our population is growing in some way. And for population growth, k is going to be positive. All right, so we've kind of unraveled what each of these little pieces of our equation here represent. Now, what about this other one in this alternate form? So we see a lot of the same kind of notation. P of t, describing our population at time t. P0, still the initial population at time t equals 0. 2 is just a constant. Little t is our variable. What is this capital T? Well, this is the time it takes for our population to double. And so in our motivating example, when we were kind of setting up what was going on, let's just pop back up there. Let's keep this alternate form in mind. So we had our initial population, and we are looking at powers of 2. So if we go back, we have our initial population, and then each kind of step of the way, we had these powers of 2. So at time 0, it was 2 raised to the 0. At time 1, when t was 1, it was 2 raised to the power 1. When t was at time 2, this was 2 squared. At time 3, it was 2 cubed. And so what we had, if we kind of relate these time values here to our kind of our data points here, what we see is that it kind of fits this alternate form. And the only thing to note is that our population was doubling in size each day. So in this case, the time it took to double, t, was equal to 1. So this was the doubling time, the time it takes for the population to double. And different populations are going to take different amounts of time to double. But in this little example, our population was doubling in size each day. So the capital T value there was 1. And so in this case, we could say that the kind of the general form for this population would be P0 times 2 raised to the little t over 1. Or we don't normally write division by 1. So this would be our formula for the population size at any time for this example. All right, so we're going to try another one. And we just want to keep in mind that there's these two formulas that we can consider. There's this exponential function with base 2, which kind of makes sense if we're talking about things doubling in size. But then we also have our natural exponential function, and it's going to be easier to talk about rates of change. So we're primarily going to be using this one, but it also doesn't hurt to keep this one in mind as well. And these two formula are really equivalent. And let's actually show that. All right, so we have a property that says b raised to the power x. So any exponential function we can write in terms of the natural exponential function, and this conversion is e raised to the natural log b times x. All right, so let's investigate this exponential function with base 2. So if we have 2 raised to the, and let's rewrite this a little bit, 1 over t, 1 over capital T times little t. So we're just going to kind of break that apart a little bit. And what we can do is we can convert this base 2 into our natural exponential function using this property. So we can take whatever is up in the exponent and we can multiply it by natural log 2. So we end up with e times natural log 2 times 1 over capital T times little t. And it's this natural log 2 times 1 over t. This is going to be our k value. And we'll be able to figure this out as we go along as well. So it's not necessary to have to memorize this, but it's just going to be helpful to recognize that our growth constant k, we can also think of this as natural log 2 over capital T, the time it takes for our population to double. All right. And so whenever we see, if we're looking at examples, let's look at example 1. And what we have in this example is a colony of fruit flies that's growing at a rate proportional to its size. And this phrase here, the growth rate proportional to its size. Actually, let's throw that in there as well. That really implies that we're talking about exponential growth. So this tells us we're dealing with an exponential growth curve. And we'll just write down the formula there. And so when we kind of see that, our terminology here is that a population is said to be growing exponentially if at every time t, the rate at which it's growing is proportional to the size. And that's primarily what this says. So the p prime up here is the rate of growth. And then the p of t that we see in the denominator is the size of our population. And so when two different quantities are proportional to each other, their ratio is equal to a constant. So the rate at which our population is changing is proportional to the size of the population. So this is all equal to, this ratio is equal to some constant k. Or rewriting this, we could multiply both sides by p of t, and we get this equation here. All right, so let's keep going with example 1. So we know that our population is experiencing exponential growth. So that means we can model its population size using our exponential growth formula. And what we're going to have to do is we want to determine a function that expresses the size of the colony as a function of time, where we're measuring time in days. So we actually want to figure out more specifics about what this formula is going to look like. All right, so when we do this, there's really two things we need to get. So first, we need to figure out our starting population. So we need to figure out P0, and then we also need to figure out our growth constant K. And that's what we're going to do. First step here, we're going to determine what the initial population is. And sometimes it's told. Sometimes we're going to have to do some calculations and figure it out. And in this case, we're specifically told that initially 20 fruit flies are present. So that is telling us P of 0 is equal to 20. So let's just update our formula so far with that result. So we're going to throw 20 in for our P0 right here. All right, so initially 20 fruit flies are present. So we know P0 is 20. All right, so now once we have our initial condition, we got to figure out the growth constant. So that's the next step. We're going to figure out K. And this is where we have to use some additional information. So we know that in 5 days, there are 400 fruit flies. So let's unravel what that means in terms of our function notation. So what that's telling us is that our population after 5 days is equal to 400. All right. Well, let's figure out what P of 5 is if we plug 5 into our formula so far. So we're going to plug 5 in. And when we do that, we're going to get P of 5. And let's plug 5 in for wherever we see little t here. We're going to end up with 20 e to the k times 5. And we know this should be equal to 400. And what this does is this gives us an exponential equation that we can use to solve for k. All right, so let's do it. Let's solve that exponential equation. So let's write it down. 20 is equal to e to the 5 times k. And I'm just going to reverse the order there up in the exponent. So I like to put the known constant first. And then this is equal to 400. And the way our general strategy for how to solve these exponential equations is we want to isolate the exponential term where our unknown variable or unknown quantity is. So we want to get this all by itself. So we're going to divide by 20. Okay, so dividing by 20, what does that give us? Well, that'll give us e to the 5k is equal to 20. So 400 divided by 20 is 20. So far, so good. Now we have the exponential term all by itself. We want to get rid of this exponential, so we want to get our unknown quantity out of the exponent. And the way to do that is we're going to apply the natural log to both sides of this equation. And when we do that over here on the left, the natural log and the e just cancel out. And this gives us 5k over there on the left and natural log 20 on the right. And then we can just finish this off by dividing by 5. And we get k is equal to natural log 20 over 5. There we go. All right, so let's fill it in, and then we're done. So we want a formula for the size of our population. So let's take this k value, and let's update our formula for P of t that we have so far. And when we do that, we end up with our initial population, which was 20, e, and then instead of k, let's fill in our k value. So natural log 20 over 5 times little t, our variable. And there we go. We have a nice formula now that we can use to describe the size of our population at any time, as long as it keeps undergoing this exponential growth. All right, so that's gonna do it for this. And what we're gonna see is there's just kind of different, there's different ways we can approach these problems based on what information we know. So we're gonna try some other examples where we try to construct these exponential growth formulas, and we'll see some other cases of how to do this. So we'll see you then. Bye-bye.